All right, let's solve an interesting question. This time it is question 206. Let's read the question. Question 206. Two long parallel wires are hung by cords of length 0.05 meter, as shown in the figure above. Each wire has a mass per unit length of 0.03 kilogram per meter, and they carry the same current in opposite direction. What is the current if the cords hang at 6 degrees with respect to the vertical? Oh, there's a lot of detail here that we need to pay attention. So first, what we're shown on the diagram is we have two current carrying wire. Now, by the way, we don't see them like this. They are shown like more in a 3D way. But if we were to see from the side, if we had the two wire in front of us, this is how they will look like. So the first current will be pointing out of the board, and the second current will be pointing into the board. We're told that because they carry a current, there will be an angle over here, so they will hang from the vertical. I cannot already tell you they will be repelled. We will see why in a moment. We are also told that I2, so the current in this wire, is equal to I2, so I1 is equal to I2. We are given the length of this cord over here. So the length of the cord is 0.05 meter. The mass per unit of length is 0.03 kilogram per meter. The angle over here is 6 degrees. The two currents are exactly the same. Now let's just simplify the force formula on two current carrying wire with the data we have. Note, since they share the same mass per unit, the same current, and the same angle from the vertical, if we solve one of them, we will get the answer for the other one. So I'm going to be solving from the point of view of the first wire over here. Before I continue, let's conclude that really they repel each other. So from the point of view of the Biot-Savart law, this current is pointing out, which means that the magnetic field will be curving counterclockwise. From the point of view of this wire, it will be pointing up. So the current here is pointing into the board, the magnetic field is pointing up, and the force will be pointing to the right from the point of view of the second wire. Well, by Newton's third law, this one has to point in the other direction. So they repel each other, all right? Just like we said at the beginning of this chapter, two wire with a different opposite direction will repel each other. All right, so let's start with the magnetic force on a current carrying wire. It is equal to the current multiplied by the length multiplied by the magnetic field. Now note, we are not given the length, we're given a unit of mass per unit length, and we will see how to deal with this later on. So we got that value. We got the magnetic field. Now the magnetic field, we use the Biot-Savart law in this case. We got I multiplied by L, and the Biot-Savart law is the permeability of free space multiplied by the current divided by 2 pi r. Now note, the distance is the same for both wire. And this distance over here, if we want to find this distance, it is the length of the wire multiplied by sine of this angle. And since we have to cover this distance twice, so the distance between the two current carrying wire is twice that value, the radius is equal to 2 multiplied by L multiplied by sine of 6 degrees. So we got a couple of values we can compute right away. So we got permeability of free space, 2 pi, the radius. Just to remove some of the value, I computed this. So it's 1.9 multiplied by 10 power minus 5. So the magnetic force is equal to the current square multiplied by the length multiplied by this term over here. Now note, we will need it later on. We can take the L, flip it on that side. So force divided by the length is equal to mass time acceleration, by the way, divided by the length is equal to the current square multiplied by this term. Now, my board is quite small, you know by now. We did plenty of force diagram. I'm gonna skip that part. The force acting on this wire over here, there's 3 forces. There's the tension, there's the force of gravity pointing down, and there's the magnetic force. Now, the magnetic force is counteracted by the X component of the tension, and the weight is counteracted by the Y component of the tension, all right? So to get the X component of the tension, we will need the opposite side of this angle, so sine of 6 degrees, and for the Y component will be a cosine. So let's repeat this. From the point of view of the X-axis, the magnetic force is pointing to the left. It is negative, so minus Fm, plus the component of the x-axis from the tension, T multiplied by sine of 6 degrees, we are told that the wire hang at a certain angle, which means they are not moving. If they are not moving, the acceleration is 0, so this is equal to 0. Same logic in the y direction, except now we're dealing with the weight. So weight of the cord plus T multiplied by cosine of 6 degrees. Again, it is equal to 0. Now note, we don't know the tension. We want to remove the tension. So tension here, if we isolate the tension, it is equal to mg divided by cosine of 6 degrees. All right, we take the T, flip it on that side. To simplify, I took the Fm, I flipped it on that side. So it's positive magnetic force now, is equal to mg divided by cosine multiplied by sine of 6 degrees. Now no, sine of 6 degrees divided by cosine of 6 degrees is tangent of 6 degrees. So that might be useful in this case. All right, so I will need some more space to write down here. So at this point, we got the value. We will need that one, so I don't need anything above. So if you need to pause the video, do it now. All right, so Fm is equal to that term over here, I squared L 1.9 multiplied by 10 power minus 6 is equal to mg multiplied by tangent of 6 degrees. One value we will need in a moment is m. The mass divided by the length is 0.03 kilogram per meter. That will be very important. So what we're going to do basically is we know this term and this term are equal. We don't know the length, but we do know the mass divided by the length. So what we're going to do is we are going to divide these two sides by L, or actually we can even take the L here and flip it on that side. Might be simpler to visualize that way. So I square multiplied by 1.9 multiplied by 10 minus 5 is equal to mLg tangent of 6 degrees in this case. All right, so at this point we literally got everything. We simply need to simplify everything. So we got that expression, and we get that the current is 40 ampere. All right, so it's an interesting problem. It combines many concepts together, and we need to understand again direction and how to calculate the magnetic field on a current carrying wire and a magnetic field from a current carrying wire. All right, so there's a little bit of geometry involved also in figuring out the distance between the two current carrying wire. All right, again, these questions are a bit more challenging. For sure, you will have one of these, a combination of what we've seen in this chapter in the final. There's no avoiding it. Make sure you practice them. If there's anything unclear, let me know. That's my job to be able to help you when you get stuck. All right, so let's go to one last example involving solenoid, and we're done with chapter 9. See you in the next video.